All right, so let me start today's webinar session. All right, I will explain about the pile modeling in Gts Nx first, before to proceed the analysis steps. Okay, so pile raft and their bearing behavior is a very good example for soil structure interaction. And if we have look here on the left side, we have a left separated from the piles. So the left itself has its own interactions with the soil around it. And the pile has interaction with the soil around this one. And there is interaction between the pile, the raft, and the piles themselves, which is a little bit summarized here on the right-hand side. And these four arrows showing the interaction. We have pile soil interaction, we have left soil interaction, and also have a left pile interaction, and also pile and pile interaction. These interactions are very critical governing how the pile raft will behave or perform and its bearing capacity at the end. The total bearing capacity of the pile raft will be the summation of the bearing capacity of the piles plus the bearing capacity of the pile raft. And the pile bearing capacity is in itself the summation of the base capacity plus the shaft capacity, and the loft bearing capacity is at the contact stress over the area of the lefts. And this total bearing capacity combined by loft should be larger than the flight loss multiplied by the factor of safety. Okay, so when we come to Gts Nx, we can model piles with three different approaches. Actually, in general, in 3D numerical tool, you should be able to model your pile as a volume element, and you should have proper interface around it to be able to capture this interaction between the pile and the soil property. So this is a basic ingredient you should have. In Gts Nx, we can do that. We can model the pile as a full volume element, soil element model with an interface around. When you have a large number of piles, a lot of piles, it can be computationally intensive. So you can think about alternatives, and one alternative to use beams representing the piles with an interface around it also. Or you can use something like we have here in Gts Nx, embedded pile or pile element, which is a rind solid, which is a beam element connected through rind to solid interface to the surrounding soil. Okay, you look close to each of these elements. So, so if we look here at the soil model, we imagine here we have a pile inserted in the soil. Pile itself is modeled with a solid element, which is a volume element filled by its full diameters and lengths of ranks. Of course, and next to the pile itself, we have 2D interface surrounding it to be able to model the soil structure interaction. And we have the solid for the soil and solid for the pile. and we have interface connecting our pile to the soil. Such a model, you have to ensure that you have nodal connectivity around the whole surface of the pile and surrounding soil and the interface as well. That means that you also have to think about refinement around the pile to be able to capture the stress equalization that may happen if you have some failure. So if you have a large model with a large number of piles, that becomes a huge model computationally, takes a lot of time, even with the hardware development nowadays. Okay, so the next other possibility is to use a beam as solid connectivity model, and here you will have solid representing soil and for the pile instead of using solid element. You will use a beam element in here. And here we have only cross section showing. So this is for visualization only, but the pile itself is actually modeled with a beam element. It's a 1D element, just right. This beam element is fully connected to the soil around. We have to have fully compatible or full nodal compatibility between this beam element and surrounding soil. And you can have an interface, so 1D interface connecting this beam element to the surrounding soil. So again, the nodal connectivity still has to be ensured. Next. So in terms of input parameters, those interfaces between embedded pile of the beam and the soil are characterized by few parameters. In principle, you have a set of springs at the shear between the beam and the soil, and these springs are two in lateral direction, so Ks, Kn, and Kt, and one along the pile axis with it, which is Ks. Okay, so the next to the stiffness, there is an ultimate shear force. Actually, the bearing capacity in this case is a sort of an input. So you determine ultimate shear force for the skin friction and also for the base capacity as an input of your model. And you will not be able to calculate the failure behavior of your piles. So this is really well suited for deformation behavior and serviceability limit state. Right. So next. So if we look more closely here, we will represent by this solid block right of the beam element, and around there is the interface, and we have the Kn and Kt, which are lateral stiffness, and we have the Ks along the longitudinal direction. So the tractions are related to the stiffness, so they equal to Qs, which is shear force divided by the length. Okay, so that means that is equals to the Ks, which is the stiffness to input multiplied by its relative displacement between the soil and the pile, and these are in the different directions. Okay, so the same goes for the base or the tip bearing capacity. You have the QB, the basement, which equals to the KB, which is the base stiffness multiplied by the delta U, and this has to be less or equal to the QB ultimate, which is a value for tip bearing capacity input again for your model. Right. So for example, you can choose from a library of cross sections, the shape of the pile, and input the dimension, and it will be calculated section properties automatically for you. Okay, so next, we have simulated this using the pile element, and we are satisfied with the behavior we could capture, the total load behavior and skin friction and the base resistance, the base bearing capacity. And we can say that we can capture in a reasonable way as an individual components. So that was satisfactory. Okay, so to save my energy to proceed the analysis step, I will just show you the behavior of high elements like this. And this is about pile connection. Normally we are using the fixed condition for the pile left or single pile to ground. And I will share this presentation file as well after today's webinar session. Okay. And let me open the Gts Nx program to proceed the advanced course. Right, give me a moment. Can you guys see my GTS NS program, what I opened? All right, I will proceed the analysis stage. Okay, so today's we're gonna conduct the analysis for the pilot Raft foundation with a single layer of the ground condition. So this starting file will be shared to you guys after the webinar session. And when you go to Mesh tab, check the materials. There are soil and materials for the Loft and pile, and the pile interface. Already key in the ultimate shear force and shear stiffness modulus. And as I said yesterday, the normal stiffness modulus using the multiplied by 10 or 100 from this stiffness modulus. Okay. And under the property, I assume the ground condition as a solid using the soil materials. And I divide the Loft and pile. Loft is assumed by Shear, and pile is assumed by beam, and interface, and pile tip. And pile tip also using the bearing capacity is 100, and spring stiffness the same as interface sys1. Right, so Let me start to create a geometry. So firstly, we need to change the work plane to XY plane. So open this work plane tree and double click this one. Right. Okay, so I will draw the rectangular for the loft. It's 6 by 6. So using this rectangular, and the first location is -6, point -6. Apply and 12, 12. Okay. Sorry about that. I think it's not 6 by 6, 12 by 12. You can directly check the length. Press the F3 key from your keyboard and click the starting point and end point. Then you can directly see the distance like this. Like this. Okay, so the next, I will create the point for the group pi. So go to point. And today I will be using the tabular input. Read from the pi. And this text document. I will share this text document as well. Let me show you what is inside there. Okay, so there are 3 values from one row, and this is X, Y, Z. It's a coordinate system. Okay, so open this one, then as you can see here, it has imported like this. And click OK. Then, as you can see here, points are imported using the table. And I will hide this grid and axis plane, working coordinate system. Okay. So the next, I will extrude this point, make it right for the piles, and using this extrude function, target. You can't select the point, so you need to change the selection method to point. So select the 9 numbers, maybe 9 numbers, yes, and Z direction, and the length is 15, and I will check on this reverse direction and give the name pi. Preview. It is correct. Okay. Okay, so just now I did create the lines for the group pi. And the next, I will create the solid for the ground. And I will use this one, the box, to create the solid. So I need to give the, I need to give the original point -60 and -60 and -30, and width 120 and 120, and height 30, and change the name ground. Preview. I think it's correct, so click OK. Okay, so just now I did finish to create the ground solid, and okay, let me hide the ground and parse for the group height, the lines. Okay, so the next I will imprint those pointers on this face, the ground surface, and also the lines also imprinted to the face for the loft. Okay, so using this imprint function, and firstly using the point tab and select the point. Need to change the selection method, or okay, or okay, type the V from your keyboard, then you can change the selection method and select the points here. Maybe it's 18, but we need to select 9 points. So select target object is a face, and select the tool object is point. So if we want to select those 9 points only on front of the ground, I will turn on this one, front selection only. Then, as you can see here, 9 points are selected. So I will check on this direction of shortest path line. Apply. And next, I will imprint those lines for the loft. Firstly, I need to select the face, the target object. The next, I will select 4 lines for the loft. And check again, this one, the direction of shortest path line. Okay. Okay, so when you hide the point and curve under here, it is not disappear because we already imprint those points and the lines on this face. So I will delete this one. Okay, parse. We need a parse line, so leave it there. Okay, so the next, I will give the mesh size, the control the size for the loft part. So select the lines, 4 lines here. And I will estimate is 1 meter of the mesh size. Okay. So as you can see here, there are red dots after control the size of mesh. So when you check the distance, okay, I think this one cannot select. Anyway, okay, so the next I will generate the mesh. So selection method to change to solid and select the solid. Right click and generate the mesh. And I will give size of mesh is 10 meter. And property is only one for the soil. And I will give the name ground. Okay. So as you can see, this area, I already gave the size control of the mesh with 1 meter. So it is around 1 meter from the node to node, the distance. And here is a 10 meter, what I gave. Okay, let me check. Maybe around 1. Okay, it's around 1 meter. Okay. So the next, I will generate a mesh for the loft. So hide the ground mesh and activate every geometry. And I will use extract function for the loft. So click extract, type, change to face, property loft, and select the face here, and give the name loft. Click OK. So there is loft on the ground surface. Okay. So next, I will generate a mesh for the piles. So I will hide this loft mesh. And for the pile, I will use this pile and pile tip function. And it is already selected the pile interface here. So okay. So before you use this pile and pile tip element, you need to generate a mesh using this 1D generation as a yesterday one. And division, I will give the 1 division and select the pi. This is the pi. Okay. Check the nodes. There are 2 nodes from each pies because I did divide only 1 element. Okay, so after that, I will use this one, the pile and pile tip element, and select the beam element, the nine numbers, and give the name pile interface. Apply. And for the pile tip, and go to pile tip tab, and see the front view, and check off this front selection only, and select tip part. Okay. Make it 9 numbers. Okay, let me check why I can select 10 numbers when I select like this. Maybe there are 2 nodes here. I found here. You need to careful to select the node for the pile tip. You need to select only pile tip part. So then that means there are 9 numbers of nodes only selected under here. So click OK. So just now I finished to generate the mesh for the ground and mesh for the loft and mesh for the pile with a pile beam and pile interface and pile tip. Right, and next, and I will merge the nodes between the loft and pile. Maybe if you are checking the nodes ID, there are 2 numbers of nodes on the 1 point between the loft and pile. That means it's not connected between the loft and pile. So I will make it connected using the merge function here. Merge the nodes and select every node, Ctrl A, fine, maybe 18, because there are 9 points on the two nodes on the 9 point. So that means 18 object, and merge. Okay, as you can see here, the 9 nodes are merged. Okay, so the next is load and boundary condition. Firstly, I will give the boundary condition for the ground first. Go to static and slope analysis tab and click this constraint. Go to auto tab and give the name BC. Okay. Okay, so the next I will make the boundary condition for the pi. So hide everything without the pi's and click constraint again and go to advanced tab. And I will check on this rotation of Z direction and pi BC and select all. Okay. Okay, so this is a normal situation of for the pi from the Gts Nx. You need to create the pi beam and interface and tip and give the fixed condition for the rotation Z direction. And the next, I will give the self rate for the stress analysis. Give the name SW, click OK. Right, so next I will give the surcharge on the loft. So I will turn on this lid first to select the face easily. And click this pressure, the face, and change the type, 3D element face. Selection method, change the face, then you can select only left face like this. Okay. And give the pressure 30 kilonewton per meter square. And name is load. Okay. As you can see here, you need to check the direction of arrow of the load. Like this is from up to down. Okay, so just now I finished to generate the mesh and define the boundary condition and load. So the next, I will define the stage, the construction stage. So go to analysis tab here, and right click on this stage set. Right click and add construction set. And I will carry out the analysis with the stress type and add. Double click this one or click this one or right click on here. Okay. So the first stage is initial stage. And make the initial ground condition, and I will change the show data to activate only. And boundary condition for the ground, self rate, and make it clear the displacement, the 0, and define the water level. If you wanna assume the flat water level, you just using this one and give the height. It is follow the coordinate system, -3. Here is a jet coordinate system is 0, and here is a -3. Okay. So the next I will install the part Raft. So part interface, part tip, Loft. You can select like this using your shift key, like this, or control, like this, shift key, control, shift key, and move to activate data. You have to move to activate data. You don't need to move to the deactivate data. Okay, so prior boundary condition, like this, and clear displacement again, save. Next. Next is apply the load. So just move this load data to activate data. Right, and save and close. After you finish to define the analysis stage, then we need to create the analysis case to perform the analysis. So right click on here, the analysis case, and click add, and give the name 3D part Loft, and select construction stage. Click the analysis control and make the initial stage to cannot condition like this. Okay, and output control. If you wanna get the load displacement graph, then you need to check on this strain to get the related displacement from the pi. Okay. Right, so just now I finished to make it perform the analysis. Okay, so right click on here and click the solve. Then it will be proceed to solve. Okay, so after this, let me open the result file. Okay, so I think it is not taking too long time. Okay, so after the performing the analysis, you can go to result tab and you can see the stages what you created under the construction stage. Right? And when you open this tree, you can see the results such as displacement and forces, and part forces, party forces. And this tangential X means shaft resistance from the pi. And under the party force, this tangential X means party bearing. Right? And if we want to hide this water level under the result, go to Analysis tab and open this stage set and check off this water level. Check off, check off. You can check off for your report. Okay, and one by one. Self-weight, load. Okay, so check the displacement first of the ground. Okay, so if we want to show the mesh, you can control under here the edge type, mesh edge. Yeah, you can see the mesh with a contour. This one is contour line, right? And smooth, you can control it like this. Okay, and deformed, undeformed, deformed. And also you can control the scale factor under here. Actual, deformed, apply. And this is the factor. And after you change something under this property window, and you have to click apply. Okay. Yeah, I will make it undeformed. Okay. The next I will show you some specific function of from the results. It's a clipping plane. Here you can cut like this. You can control to move. Add this one. Add. You can control it like this. Okay. Like this. I think it is very useful to show on your submission report to check the inside contour. Right? If you want to turn off, just turn off. Turn on, turn off. Okay, so the next, I will check the bending moment of the loft. So loft, I assumed by shell element. So go to shell element forces, double click this one, and you can see the bending moment and membrane forces and shear forces. And I will check the bending moment first, and using nodal average, like this, X, Y, 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 X. Okay, so the next I will check the forces from the pi. So I will hide every meshes without the pi. That means only show the pi's. Okay, so go to result again. And this part is assumed by beam. So if you want to check actual force, shear force, bending moment, like this. And as the last time, if you want to check the shaft resistance, go to pi force and double click tangential X, like this. It's shaft resistance and bearing under the pi force. All right, so this is the advanced session of the part left analysis with the Gts Nx. And let me open the presentation to finish today's session.